Welcome back to my channel. In continuation with the class 11th CBSE Chemistry final exam preparation series, I've already uploaded 6 videos on mole concept, which covered the various aspects like scientific notation, significant figures, limiting reagent, empirical formula, concentration terms. Everything of the first chapter was covered in 6 easy videos for your last moment revision of the chapter. So today I'm going to start with atomic structure. The first video is going to cover up models, atomic number, and all the important questions from each topic that can be asked. Like I'll suggesting to you the question and then what are the points to be included in that. So I advise go through the video alongside, keep learning the content and keep highlighting in your NCERT textbook. Take notes, brief notes. Don't waste time. You can keep either your notes copy in front of you where you've already done atomic structure, or you can keep NCERT in front of you and just keep highlighting the points that need to be learned and need to be revised even one day before the exam. Right? So stay tuned. Let us quickly start. So this chapter has a weightage of 9 marks for your final exam. And the first topic is subatomic particles. Under subatomic particles, it begins with discovery of electron. So what are the important things that can be asked? The construction of this cathode ray discharge tube, a very quick look into. We have cathode, anode. Anode is a positive electrode, cathode is a negative electrode. And very important point that you need to understand, which can be asked in MCQs, high voltage and low pressure is required for cathode ray tube experiment, and low pressure is created by using a vacuum pump. Low pressure means sucking out air using a vacuum pump so that very few air molecules are left inside for conduction of electricity. You know, gases are poor conductors of electricity at ordinary pressures. Hence, vacuum pump needs to be connected in order to create low pressure. The anode is coated with a fluorescent screen, which is a zinc sulfide screen, in order to observe the cathode rays. So as the cathode rays start from cathode, hit the anode, we observe them on a zinc sulfide screen. And hence the zinc sulfide screen is called as a fluorescent material. We have a perforated anode in order to facilitate the cathode rays to pass through and be observed on the anode. So these are the experimental components. Cathode rays discharge tube with perforated anode. Now, what are the important points that you need to understand? Cathode rays flow from cathode to anode. They are invisible, can be observed by making a hole in the anode, coating it with a phosphorescent or a fluorescent material such as zinc sulfide, and these rays passing through anode strike the zinc sulfide screen. As a result, a bright spot develops on the screen. And the next question that is probable, either as MCQs or a 1 mark question, the principle involved in a television set. So television set works on the principle of cathode rays, the invisible rays. In presence of electric fields, these are attracted towards positive electrodes similar to negatively charged particles called electrons. This helped to conclude that cathode rays are made up of electrons. Cathode rays do not depend on nature of cathode or nature of gas. A very important statement for questions. Do cathode rays depend on nature of cathode or nature of gas within the discharge tube? The answer is no. Why? Because irrespective of the material used to make cathode or the gas used, since they give out electrons, since cathode rays are made up of electrons and electrons are the universal constituents of all matter, so it doesn't make a difference electrons have been released from which gas or from which surface. They will always have the same nature. Hence, cathode rays do not depend on the nature of either cathode or the gas. The next point of importance is the charge to mass ratio of electron. The things that you need to know about this topic. Charge to mass ratio of electrons. This was studied by J.J. Thomson. Again, using the cathode ray tube experiment. He used a cathode ray tube and applied So I have highlighted the points that you need to keep in mind. Applied electric and magnetic fields which were mutually perpendicular to each other as well as to the path of electrons. So if this is the path of electron, this is the magnetic field, this is the electric field. So the three path of electrons, electric field and magnetic field all were in mutually perpendicular directions. So these kind of points are needed in case multiple choice questions are asked. So apparatus used to determine the charge to mass ratio, that is E by M ratio of electrons, is this modified cathode ray discharge tube where we have an anode, a positive electrode, we have a cathode, this is the cathode, then a magnetic field is applied, that is the north and south of a U-shaped magnet, and then we have an electric field and a fluorescent screen. The electric field, this is the electric field, positive and negative terminals. This is the magnetic field, both are in mutually perpendicular directions, and this is going to be the flow of electrons, again perpendicular. So three flow of electrons, this is the electric field and this is the magnetic field. These are three mutually perpendicular directions. So this anode is perforated, a fine beam of light of cathode rays starting from cathode, moving towards, attracted towards anode, and in presence of an electric field alone, in presence of an electric field alone, the electrons get attracted towards the positive electrode, that is anode. Why? Because electrons are negative charged and cathode rays are made up of electrons. So in presence of an electric field, get attracted towards anode. This is the point to be kept in mind. And in the absence of electric and magnetic field, the cathode rays go straight. And in the presence of a magnetic field, they again get attracted towards one pole, which is decided by Fleming's left hand rule, right? So, what was the basic principle on which this experiment was based? The amount of deviation of particles from their path in the presence of electric and magnetic field depends on amount of deviation of particles. Which particles? Cathode ray particles. Cathode ray particles. The amount of deflection dependent on which particular components, magnitude of negative charge on the particles. More is the negative charge. In general, more is the charge, more is the deflection of any charged particle in an electric or magnetic field. And you can understand it like this also. A lighter particle flows faster. So lesser the charge, lesser the deflection, more the mass, lesser the deflection, right? More charge is more attraction, more deflection, more mass. A heavier particle means can flow less, so less will be the deflection. So what are the 3 points that are of importance? One, higher negative charge, higher deflection. Second, lesser mass, higher deflection. Third, greater is the strength of electric or magnetic field, greater would be the deflection. So using some mathematical formula which are beyond the course content of your limits, Thomson had calculated the charge to mass ratio. So when only electric field is applied, electrons deviate from their path and hit the cathode ray tube at point A. As we've seen in the previous experiment, on balancing both electric and magnetic field, the path of electron can be made a straight line. That is, they hit the zinc sulfide screen on the cathode ray tube at point B, and when only magnetic field is applied, the electrons deviate from their path and hit the cathode ray tube at point C. We just observed these particular points in the previous figure. So this is point A. Only electric field getting attracted towards anode. This is point C, only magnetic field. And when either none of the two fields is there or both are balanced, then it moves to the point B. This is what we are trying to explain here. And these are all strictly NCERT lines. So charge on the electron we know is 1.602 into 10 to the power minus 19 coulomb. Now, by calculating the strength of the field applied and the extent of deflection, the charge to mass ratio was calculated experimentally. And charge to mass ratio, that is E by M ratio, that is charge per unit mass, is also called as specific charge on the particles. So E by M ratio of cathode ray particles, which are also nothing but electrons, was calculated to be these values. 1.7588, 2 into 10 to the power 11. Please remember the unit coulomb per kg. The charge on electron is 1.6 into 10 to the power minus 19 coulomb. This is the value of charge in SI unit. This is the value of charge in SI unit. And mass of electron in SI unit is 9.1 into 10 to the power minus 31 kg. These are SI units. What is the charge on an electron? Just remember, the experiment to find out the charge on an electron was calculated by Millikan. And Millikan devised the oil drop experiment for this. So you can be asked a 1 mark question: who devised and using which experiment was the charge on an electron device? The answer is Millikan's oil drop experiment helped to calculate the charge on an electron. So we have a charged plate. Here we have a negative charge. Basically, this container is divided into different chambers. There's a small hole made in the central compartment, and there's a source of X rays, and a fine atomizer is used here. So, using an atomizer, oil drops are sprayed using an atomizer. And we have a telescope with a micrometer eyepiece just to observe what is happening, and a source of X-ray to ionize the gas. This is a source of X-ray from this side. This is going to ionize the gas and create electrons, and these electrons are going to get trapped on the oil droplet. These are the oil droplets. Just one oil droplet is going to manage to pass through this small hole into this space, and here X-rays are going to ionize the gas present here, air present here, and electrons will be released. And these electrons will get trapped on this oil droplet, making this oil droplet charged. So when this oil droplet is charged, that's a very random process. That means the charge could be 1 unit of negative charge, or it could be 2 units of negative charge if two electrons get retained on it. So according to that, the many experimental observations were taken to finally calculate the actual charge on the electron. By carefully measuring the effect of electric field strength on the motion of oil droplets, Millikan concluded that the magnitude of electrical charge is always an integral multiple of electrical charge E, that is Q is equal to NE. I am just elaborating this point, children. When this oil droplet was made to pass through a hole in this chamber, and the oil droplet got covered by one or more electrons, the oil droplet became charged. So this oil droplet is going to move downwards under the force mg, its own mass and gravity. Clear? And here we had a negative plate. Electrical potential is applied here with a minus terminal this side and plus this side. So this minus is going to repel this charged oil droplet upwards. This positive plate will attract it upwards. This negative plate is going to repel it upwards, and its own weight mg is going to drag it down. Plus, there'll be some viscous force, etc. Right? So, taking into account all these forces, some calculations, mathematical calculations were done. And finally, we don't have to get into the details of those mathematical derivations. You just have to remember that total charge on an electron was found to be a whole number multiple of some unit charge, some fixed charge value, which was the charge on electron. So in the chamber, forces acting on the oil droplet were gravitational forces, electrostatic forces. Again, a 1 mark question. What were the forces acting on the oil droplet? Gravitational forces pulling it downward, electrostatic forces repelling it upwards, as I've already explained. Right? So, based on this, the charge to mass ratio, the charge on the electron was calculated. Now, discovery of protons and neutrons. How was the discovery of protons and neutrons done? Again, it was done in a modified cathode ray tube. Now, basically, what was observed, if this is the cathode ray tube, this is the cathode ray tube, and this is the cathode, this is the anode. So, certain kind of rays which started from cathode were called cathode rays. These cathode rays, when they hit the gas particles present in the cathode ray discharge tube, managed to ionize these particles, liberating some positively charged particles along with some more electrons. So, these electrons which started from cathode and the electrons which were formed by ionization of the gas, they all started moving towards anode. And this stream of fast moving negatively charged particles, electrons, was what we called as the cathode rays. So, since cathode rays start from cathode as well as they originate from the gas inside. So, if a question is asked from where do cathode rays originate, you would say cathode rays originate from the cathode as well as from the gas within, right? But anode rays are composed of positively charged particles. They are not only protons, they are positively charged particles. Depending upon the mass of these particles and the charge on these particles would depend upon the nature of gas. So all these would start moving in the opposite direction, getting attracted towards cathode. So these were called as anode rays. Why these positively charged particles constituted anode rays? Because they were appearing to be originating from anode. They appeared to be originating from anode, right? They were not actually starting from anode, but since they were moving towards cathode, it was thought that they start from anode. So please be careful. Anode rays appear to be coming from anode, they do not originate from anode. So, do anode rays originate from the gas within? Yes. So, I summarize this point. Cathode rays, what is the origin? Origin of cathode rays is cathode and the gas within. Whereas for anode rays, the origin is only the gas within. Okay, so cathode rays are made up of negatively charged electrons, whereas anode rays are made up of positively charged particles, which may be a single proton if we are talking about hydrogen gas, or it may be made up of positively charged particles, each having many protons. Right? So please remember these can be again potential questions in the form of MCQs otherwise. So nature of positively charged particles depends on the nature of gas present. But did the nature of negatively charged electrons or cathode rays depend on the nature of gas? No. Why does this anode rays depend on nature of gas? Because let us suppose if the gas is oxygen and this loses an electron, it is going to form something like this or this. These kind of species will be present inside the discharge tube. But if it is composed of something like nitrogen and it loses an electron, then it is going to be composed of this or this, right? And each of these species is going to have many protons and many electrons in it, not just one proton. But in case we are taking hydrogen gas, this when loses electron is left with just H plus, right? And this is nothing but this is a species having just one proton. So only when the gas inside the discharge tube is hydrogen gas, we can assume that anode rays are made up of protons. I hope this point is clear. And why are these called as canal rays? Because as they flow within the discharge tube, they give the appearance of a canal, hence known as canal rays. Okay, so E by M value of positive rays or anode rays is not similar to that of electrons, and it is also not constant. Its value depends on the nature of gas. Again, a very important question here, very important to understand. Cathode rays have constant E by M, it's fixed, it doesn't change with the gas used. Whereas anode rays, E by M changes how it depends on the nature of gas used. Very important difference for questions. So next we come to the values of mass of proton and charge on a proton. Charge on proton is the same as charge on electron, just with a difference of sign. And E by M value of proton hence is the charge upon the mass. And we have this value in coulomb per gram as well as coulomb per kg. If you're asked to give this value in SI unit, it is coulomb per kg. You have to cram this value, right? And this has been written for in CGS unit. This is the CGS unit. The CGS unit of charge. CGS unit of charge is ESU, the electrostatic unit, and the value of electronic charge on CGS unit is these many ESU. On SI unit, it is these many coulomb. On CGS unit, it is these many ESU. So dividing this charge by mass, we get in the value of E by M in CGS unit. Yeah. Now, discovery of neutron, just remember the names. Discovery of electron was by Thomson, proton by Goldstein, and neutron by Chadwick. Again, these are 1 mark questions for your exams, you must keep in mind. And then this is the NCERT information about how the neutron was discovered. The discovery was done by bombarding a thin sheet of beryllium by an alpha particle. So the experimental part can be asked in the form of MCQs. What is alpha particle? It is doubly ionized helium ion, or you can say it is helium nucleus. So what is the difference between helium atom and helium nucleus? Helium atom means two protons, two neutrons, and two electrons. But helium nucleus means only two protons and two neutrons, which means a doubly charged helium ion is the same thing as alpha particle. So alpha particle is nothing but a doubly ionized helium ion. It's not same as helium atom. So you must know this. What is an alpha particle? So the discovery of neutron was associated with beryllium bombarded by an alpha particle in the process forming carbon 612 and a neutron. Remember, this is a nuclear reaction. In nuclear reactions, the product is not always same as or made up of the components that you find in the reactants. Like for example, when we are talking about chemical reactions, hydrogen plus chlorine will always give us HCl. But in nuclear reactions, beryllium attacked by alpha particle is giving us an altogether new element, that is carbon. Along with the process, neutron, a neutral entity, is given out. Right? And remember, these equations always follow the law of conservation of atomic number and mass number. So law of conservation of atomic number means 4 plus 2 6. Here 6 plus 0 is 6. So here 9 plus 4 is 13. So here 12 plus 1 is 13. So the sum of atomic numbers of reactants should be same as that of products, and sum of mass numbers of reactants should be same as that of products. If you make a mistake, you can cross check yourself using this principle. Aluminium plus alpha particle gives us phosphorus plus neutron. So these two reactions were used for discovery of neutron. Neutrons are neutral. How was this established? They are not deflected by magnetic or electric fields, indicating they are neutral particles. Right? What is the mass of neutron? It is found to be slightly higher than that of a proton. A neutron is slightly higher than that of a proton. And this is the mass given, E by M value given. It's 0. Why? Because the charge on a neutron is 0. Clear? And you can also memorize it like this. Mass of a proton is 1837 times mass of an electron, whereas mass of a neutron is 1840 times mass of an electron. Right? So there's a very small difference in the mass of proton and neutron, but a neutron is slightly heavier than a proton, and both these are much heavier than that of an than the mass of an electron. Just remember this. Coming to atomic models, so after the discovery of the three particles, the subatomic particles, electron, proton, and neutron, came up the atomic models. Atomic models are going to tell us about the arrangement. They will tell us about arrangement of these subatomic particles in an atom. So different models were proposed. The first one. So I'll again be telling you in brief about what kind of questions can be asked from each model. Thomson model of an atom. What did J.J. Thomson propose? Atom is spherical. It is not circular. It is spherical in shape. Radius of an atom is approximately 10 to the power minus 10 meter, which is 1 angstrom. Radius of an atom, and the positive charge is uniformly distributed throughout the sphere, which is not valid anymore. Positive charge is uniformly distributed. Electrons are arranged in such a manner to give the most stable electrostatic arrangement. These were the postulate of Thomson's model. If you're asked what are the postulates or what are the important points about Thomson's model, you will answer these. And then this is the Thomson's model. The entire uh, published area, this area is all the positive charge, and in this are electrons embedded in a manner so as to uniformly distribute the charges. So sphere of positive charge having electrons embedded, and J.J. Thomson also compared his model with plum pudding model. This is also called as a plum pudding model, where plums are the electrons and pudding is the positive part. Similarly, raisin pudding model and watermelon model. In watermelon also the pulp represents the positive part and the black seeds represent the electrons. Fine. So what were the drawbacks? It could not explain the stability of an atom based on experimental results. And the most important, Rutherford's alpha ray scattering experiment could not be explained based on this model, and hence this model was discarded. Next is the discovery of X-rays. Now, this is given in a box in the chapter after J.J. Thomson's model. So, everything, children, that I'm discussing in this is from NCRT. So, this is the major concern is your class 11th finals, but this will be very helpful for JEE and NEET also, because the first level learning should always be NCRT based. So, I have covered in this video all the important points that can help you. And before we continue further, please do subscribe and like the video, right? Okay. So X-ray discovery is the next one. This was proposed by Röntgen using a Coolidge X-ray tube. You don't need to go into details of this X-ray tube. Uh, Röntgen discovered X-rays. Now, when cathode rays strike the target node, this is an important point that you can understand, that you can learn. This can be asked in the form of a multiple choice question. When were X-rays discovered? When cathode rays strike anode, some unknown rays were observed, which were called as X-rays because their nature was not known at the time. Röntgen did not know the properties of these rays emitted from the target node, so called them X-rays. And X-rays are powerful electromagnetic radiations. The point to focus on is these are EM radiations, electromagnetic radiations with very short wavelengths, nearly zero point 0.1 nanometer. And you know 1 nanometer is 10 to the power minus 9 meter. X-rays, what are the important points about X-rays? The ones which are quoted in NCRT and which can be asked as questions. These are the important statements about X-rays. X-rays have high penetrating power. High penetrating power, hence are used for study of interior structure of atom or matter. And this is the reason why X-rays are used to assess fractures, right? X-rays are not deflected by electric and magnetic fields, and X-rays are high energy radiations. High energy radiations and can cause ionization readily. These are the points that you must remember regarding X-rays. Radioactivity and observations of Rutherford's model. Who observed the phenomena of natural radioactivity? Again, remember the name Henry Becquerel. X-rays by Röntgen and natural radioactivity by Henry Becquerel. Substances which emit radiations on their own, that is, show the property of radioactivity, are called radioactive elements. So, what is basically radioactivity? Substances which emit radiations on their own, that is, spontaneous emission of radiations, is what we call as radioactivity or radioactive radiations. Examples: uranium, thorium, radium, francium. Observations regarding radiations emitted by radioactive elements. So, there are three kinds of radiations observed from natural radioactivity. Substances which are naturally radioactive. Remember, substances which are naturally radioactive, they give off three kinds of radiations, that is alpha, beta, and gamma. So, we're going to talk of the nature of these three kinds of radiations. The alpha rays, as we've already talked of, are nothing but doubly ionized helium nuclei. Nuclei is a plural for nucleus. One single is nucleus and many nucleus are called nuclei. So alpha rays are doubly ionized helium nuclei, that is, have 2 units of positive charge and 4 units of mass. Right? We express it as helium 2 for 2 units of charge and 4 units of mass. They cause ionization of gases because they are charged particles. They are composed of charged species. These are charged species, hence can cause ionization. They have less penetration power. They can penetrate only a few centimeters in air and hence are less harmful. Are deflected by both electric and magnetic fields. Why? Because they are charged and they are deflected towards negatively charged plate in electric field. Again, why? Because they themselves are positively charged. Now, two things you must remember, children. Less massive, that is, lighter particles have more penetration power. Lighter particles have more penetration power, and heavier particles have more ionization power. They are more ionizing. So we can observe alpha particles are massive particles. If we compare alpha, beta, gamma, alpha particles are massive particles. Due to more mass, they are highly ionizing. But since they are heavy and more charge, they have less penetration power. Since they are heavy, they have less penetration because less massive things can penetrate more. Okay, so just remember these 2 points. More mass is more ionizing and less penetrating. So, exactly on the same lines, if we think of beta rays are nothing but electrons. Okay, these are negatively charged. These are simply, you can say, electrons of nuclear origin. Okay, beta particles or beta rays. So they have a charge -1 and they are having zero mass. That means they're very light particles, negligible mass. So beta rays are negatively charged. Since they are negatively charged, they bend towards a positive plate in an electric field. They travel with higher velocities compared to alpha rays and they are having less mass. So less mass and more velocity means penetration power of beta rays is going to be 100 times more than alpha rays. I told you light and more velocity will pierce through, will have more penetration power. But something which is heavy is going to have more ionization power. So next we have gamma rays. Gamma rays are high energy radiations with lower wavelengths than X rays. Okay, with much lower wavelengths than X-rays, and hard X-rays have high penetration power and are also called gamma rays. they have wavelengths similar to gamma rays. And then the important point we have here is gamma rays have highest penetration power. Why? Because they are neutral and are a part of electromagnetic spectrum. They have high speed and no mass. So these have highest penetration power in comparison to alpha and beta rays. So these were the specifications of alpha, beta, gamma as according to NCR. So if we compare now, so penetration power, if we compare, alpha rays have least and followed by beta and then gamma. Gamma rays are massless, chargeless. Beta rays have negligible mass, but alpha rays are massive. So penetration power is maximum when there is no mass, no charge. This is also no mass, but massive particles have less penetration power. So this is the order of penetration power. Gamma rays are most harmful to biological species. Again, can be asked as a one mark or a multiple choice question. Which of the following is most harmful? Why they are harmful? Because they have the maximum penetration power and can cause mutation in biological species. Alpha, beta, and gamma rays, all three of them affect the photographic plates, and maximum effect is shown by beta rays. Why? Due to their highest E by M ratio. Each of these points, children, are a potential question. So, coming to Rutherford's nuclear model of the atom. Now, Rutherford's model is one very important model, and questions can be asked in three, four components. The first one is explain the experimental components. So, Rutherford and his students, Geiger and Marston, bombarded the main components, a thin gold foil of thickness about 100 nanometer with alpha particles. The main points about the experimental component. Then a stream of high energy alpha rays was directed at a thin foil of gold metal. Thin foil of gold metal was needed. Why? So that the minimum number of atoms or layers of atoms are included, uh, because so that we have simpler results. And why gold was chosen? Because gold is highly malleable. It can be uh, beaten down into very fine sheets. The thin gold foil was taken in the form of a circular fluorescent zinc sulfide screen in order to get observations of all the deflected alpha particles. So whenever alpha particles strike zinc sulfide screen, they cause a glow, that is flash, and from there it became easy to study the uh, deflections by various alpha particles. So this is the experimental part. This is a lead block with a cavity containing radium or polonium. Radium or polonium are radioactive materials which spontaneously, that means on their own, emit alpha particles. So this is basically a source of radiations, alpha rays. And then we have a lead plate with a narrow slit. Why narrow slit? So that a very fine ray of alpha particles passes through it. And then we have this gold foil in the form of a circular. This is a circular zinc sulfide screen. In the center of this, we've kept a very thin gold foil. So when alpha particles strike the gold foil, alpha particles emitted out are going to hit the zinc sulfide screen at different angles. And since every hit causes a fluorescence, so the points could be observed. And from there, observations led to creating a model, the nuclear model of the atom, right? So the experimental part, these are the observations. First, we have the experiment. So what were the main points of the experiment? Source of alpha particles, then a circular zinc sulfide screen, which is fluorescent, and then we have a gold foil, thin gold foil, and a lead plate just to allow a single stream of alpha particles to pass through. Right. Now, these are the observations. Again, the NCRT figure, this is telling us alpha particles, these are atoms. These are all atoms shown. And as alpha particles hit, they undergo different kind of deflections. Depending upon where they hit, they are showing different deflections. If they hit directly on this positive nucleus, then the deflection is very large. They're almost retracing their path. And in case they pass through the empty space, they are passing unaffected. And if they are passing closer, they get deflected by certain angles. So all these observations were put together, and these are the observations that you have to learn. If you're asked, write observations of alpha ray scattering experiment, these are the three main observations that you have to give. And I've highlighted the key points. Most of the alpha particles pass through the gold foil undeflected, right? Small fraction deflected by small angles, and very few, just 1 in 20,000, retrace their path. So these are the observations. Based on these observations, what were the conclusions drawn? So since most of the alpha particles went undeflected, so most of the space in the atom is empty. The green are the highlight points of conclusions. Since a few particles bounced back by large angles, this indicated highly dense, positively charged center in a small volume, right? And which causes repulsions to the incoming alpha particles. And the third point was the central part of the atom, hence, where the entire positive charge is concentrated, is called the nucleus. So these are the three conclusions. These are the three conclusions. Before this, we did the observation, and before that, the experiment. Experiment tells us what are we doing, then what did we observe, and finally, what do we draw out as the conclusions, right? So an electron is revolving around the nucleus, and there's a lot of empty space. This is what Rutherford had suggested. The radius of the atom is about 10 to the power minus 10 meter, and which is 1 angstrom, and radius of the nucleus is about 10 to the power minus 15 meter. Just to get an understanding of this, your NCRT explains that if you consider a cricket ball to be the nucleus, just the size of a cricket ball to be the nucleus, then a radius of 5 kilometer, if it's chosen and a circle is drawn, this represents an atom. So you can just visualize uh, the radius of the atom is like 10 to the power 5 times that of the radius of the nucleus. This is just for you to be able to visualize that we have a very, very small positively charged center, a lot of empty space, and electrons revolving around the nucleus. So based on this, now the fourth component is what were the postulates of Rutherford's model. After the experimental part, then the observations, then the conclusions. These are the final postulates of the model of the atom. And the postulates say the positive charge, and most of the mass is concentrated in an extremely small region called nucleus. Nucleus is surrounded by electrons, and electrons revolve around the nucleus with very high speed in circular paths called orbits. These are not well defined paths, but these are circular paths called orbits. Electrons in the nucleus are held together by electrostatic forces of attraction. These were the postulates of Rutherford's model. Now, Rutherford's model, another important thing was he compared his model to the solar model, the solar system, and in which he compared nucleus to sun and electrons to the planets. The only difference was solar system doesn't have charged bodies, whereas Rutherford's model had charged bodies. Okay. So what is this trying to explain? This is going to explain the drawbacks of Rutherford's model. So according to Clark Maxwell, when Rutherford's model was proposed, that time Clark Maxwell's electromagnetic theory of continuous generation of radiant energy was prevalent. So according to Maxwell, charged particles, when accelerated, should emit electromagnetic radiations. Now, accelerated, anything that is moving in a circular path is showing accelerated motion, because at every point the direction is changing, even if the speed is constant, right? So charged particles, when accelerated in a circular path, should emit electromagnetic radiations. So when they emit radiations, the electron in an orbit, after it emits radiations, the energy carried by the radiation comes from electronic motion. And gradually what happens, after continuously losing energy, the electron finally gets spiraled into the nucleus. The electron takes only 10 to the power minus 6 seconds to spiral down into the nucleus. The orbit will thus continue to shrink. So, stability of the atom could not be explained satisfactorily. So he could not, Rutherford could not explain how the electrons are arranged around the nucleus, and he could not explain the stability and the energies of the electrons. And then it could not even explain hydrogen spectrum. Hydrogen spectrum is a discontinuous spectrum, but according to Rutherford's model, it should be continuous, which could not be justified by Rutherford's model. Right? So just putting a little more explanation into it. Uh, Clark Maxwell's theory suggested that when an electron is revolving around another charged body, that is nucleus, it continuously emits energy. Continuously emitting energy means you can just imagine it's like getting exhausted, and it's every time its path is becoming shorter, and at a particular point it gets attracted by the trapped by the nucleus, because electron and nucleus are oppositely charged, and this entire thing takes 10 to the power minus 6 seconds. Fine. So Rutherford could not explain the stability. The main points that played a major role in the development of Bohr's model were dual character of electromagnetic radiations, that is both wave nature and particle nature, and experimental results regarding atomic spectra, which can be explained by assuming quantized electronic energy levels. These 2 points we are going to cover in the next video. The next topic is atomic number and mass number, which is a very simple topic. You have done a number of times this topic even in 10th standard, but I'll just quickly speak the kind of questions that can be asked. Atomic number, you must understand, is the number of protons. And since an atom is electrically neutral, so it is also equal to the number of electrons outside the nucleus. Clear? So for a neutral atom, number of protons is equal to number of electrons. So atomic number is basically by definition the number of protons. If the species is electrically neutral, it will also be equal to number of electrons. Okay. So what is mass number? Mass number is the sum total of both neutrons as well as protons. Mass number is always a whole number. Atomic mass is fractional due to presence of isotopes. The concept of isotopes was proposed by Soddy. Now, what does this mean basically? Children, if I talk about chlorine 1735, as we did in one of the lectures of mole concept as well, chlorine 1735 and chlorine 1737. These are the two isotopes of chlorine. So each has a mass number which is a whole number, right? But if I calculate the average atomic mass, I'm going to calculate it as 35 into 3 plus 37 into 1 upon 4. Why? Because this is the fractional abundance of these isotopes. This comes out to be 35.5. So atomic masses are fractional, can be fractional, whereas mass number is a number of neutrons and protons which can never be fractional. It's always a whole number. So 35 is the mass number, 37 is the mass number, but 35.5 is the average atomic mass. Clear? So you already know what are isotopes. These are atoms of the same element with the same atomic number but different mass numbers or atomic masses. And isotopes also differ in number of neutrons. Isotopes differ in physical properties but show similar chemical properties due to same electronic configuration. Difference in physical properties but shows similar chemical properties. Why? Because the electronic configuration is same. Why? Because electronic configuration is written on the basis of atomic number. Like for example, if I'm talking about chlorine 17 and 35 and chlorine 17 and 37. So the configuration here is 287. Here also it's 287 because configuration is written on the basis of atomic number, and two isotopes have the same atomic number. So they have identical chemical properties. Three important isotopes as quoted in your NCERT as well for hydrogen are protium, the normal hydrogen, deuterium expressed as H12 or D12. This is called as heavy hydrogen, and then the radioactive hydrogen, that is tritium. And normal hydrogen is present to an extent of 99.985. Deuterium is only to an extent of 0.015. Tritium is present in traces. So, based on this information, if I try to calculate the average atomic mass of hydrogen, what am I going to do? I'll write this hydrogen is 111, this is 12, and this is 13. So what am I going to do? 1 into 99.985 plus 2 into 0.015 plus 3 into 7 into 10 to the power minus 16 upon 100. This is what we are going to do. So this value can almost be ignored because it's going to be too small. And when you calculate the net outcome of this, it comes out to be 1.008. So why is the average atomic mass of hydrogen equal to 1.008? That is very close to the normal hydrogen because its relative abundance is too high in comparison to the other two isotopes. Also, half-life of tritium is 12.33 years. What is half-life? This is the time in which a radioactive element becomes half of its original. So tritium in nature on its own is going to continuously keep on emitting radiations and decaying. For example, if its half-life is 12.33 years, it means if today I have 1 gram of tritium, then after 12.33 years, I'll be left with only zero point 0.5 gram. We have not used it, we have not done anything, but in nature it keeps decaying on its own. Similarly, in the next 12.33 years, it will be left to 0.25. This is what we mean by half-life period. So here we have the different isotopes. I have written the atomic numbers, that is the number of protons in each, which is 1, 1, and 1. The mass number is 1 for this, 2 for this, and 3 for this. So number of electrons is equal to Z, protons is equal to Z, and then we can calculate the number of neutrons in each case, and from there the N by P ratio. This is the N by P ratio of hydrogen, deuterium, and tritium. So highest N by P ratio of all the elements in the periodic table is that of tritium. This is a point to be kept in mind. And the only element in the periodic table which does not have any neutrons is hydrogen, protium. Protium is the only element in the periodic table to have no neutrons. So these are examples of isotopes of carbon, isotopes of chlorine. Very simple. We've done this so many times. So you can just have a look. Symbolic representation of element goes like this. Either this way, XZA, or it can be on the same side, XZA. This is atomic number, number of protons. This is mass number, that is number of protons plus neutrons. So you have number of questions in the NCERT exercise based on this, such as supposing, let us say they can ask you what are isobars. What are isobars? Atoms of different elements. Now isotopes were atoms of same element. Isobars are atoms of different element with same mass number and different atomic number. Fine. So isobars, we have argon, potassium, and calcium. With this, these are different elements with the same mass number but different atomic number. And from here you can calculate Z. Z of each, that is number of protons, is also equal to number of protons and also equal to number of electrons in a neutral species. And this is 40. This is mass number. 40 is mass number. And the number of neutrons is mass number minus atomic number. While mass number is basically number of neutrons plus protons. And Z is basically number of protons. So when you do this, you will be left with number of neutrons. So 40 minus 18 is 22, 40 minus 19, 21, 40 minus 20 is 20. Okay. So if a simple question is asked, they can give you any such symbol and ask you about the electrons, protons, and neutrons. Like in this case, calculate the number of neutrons, protons, and electrons in this component. And this is a very, very simple question. Since Z is 35, you know electrons and protons are 35. Mass number is 80. So 80 minus 35 is 45. So hence the answer. So this is important. In this question, you are given the number of electrons, protons, and neutrons in a species X are this. Just the fact that the electrons and protons are not the same, electrons are more than the protons, means it must be a negatively charged species. Since we have two extra electrons than the number of protons, it means it will have a total two negative charge. More positives, 18 plus and only 16 minus. Sorry, this species has 18 electrons. That means minus 18, and 16 protons means plus 16, right? And 16 neutrons, but neutrons don't contribute to charge. So the net charge is going to be minus 2 here. And then Z, that is number of protons, is equal to 16. So we've written 16 here. And A, that is mass number, is number of neutrons plus protons, which is 16 plus 16, that is 32. So questions as simple as this can also be asked for your school exam. So the next is NCERT exercise question. This is the NCERT exercise question. An ion with mass number 37. Mass number 37 means number of neutrons plus protons is 37, possesses 1 unit of negative charge. Okay, 1 unit of negative charge means the number of electrons is more than number of protons. If the ion contains 11.1% more neutrons than the electrons, then find the symbol of the ion. So how are we going to proceed with this? Let the number of electrons be X. Number of neutrons is going to be, if number of electrons is X, 11.1% of X plus X is the number of neutrons. The question says the number of neutrons is 11.1% more than electrons. So if number of electrons is X, then 11.1% of X you add to X, you will get the number of neutrons. So when you solve, you get number of neutrons to be equal to 1.11x. We also know that mass number is equal to proton plus neutron, and protons have to be equal to x minus 1. Why? X is the number of electrons. X is the number of electrons. And since the species has a negative charge, this means protons should be 1 less than the number of electrons. This we did on the last screen. It says this has 1 unit of negative charge, which means if number of electrons is x, number of electrons is equal to x, obviously number of protons should be x minus 1. Only then we will get a negative charge if number of protons are less than the electrons. Fine. An ion contains 11.1% more neutrons than the electrons. So what will be the number of neutrons? It is going to be 11.1% of X plus X. Okay. So now we have to calculate the value of mass number. We also know the ion with mass number 37. What is the meaning of mass number 37? Mass number 37 means number of neutrons plus protons. So what is the number of neutrons? This came out to be 0.111x plus x, that is 1.11x. So number of neutrons is this, plus protons is x minus 1. Yeah. So this is going to be how much? 1.11x is 37. So from here we are going to calculate the value of x. So when you solve this, x comes out to be 38. If X is 38, that means number of electrons is 38. Number of protons will be 37. So mass number, that is A. Mass number A is 37, which is given to us. We have calculated number of electrons to be 18 and number of protons to be 17, right? This is what we have already covered. So this is going to be our final answer. So this is 18, number of electrons 18, number of protons 18 minus 1, 17. Hence the symbol of the ion becomes 17 is Z, A is 37, and there will be a negative charge. This is NCERT exercise question. Please practice it well. There's a big scope of this being asked. And another NCERT question, an ion with mass number 56 contains 3 units of positive charge. 3 units of positive charge, which means number of protons has to be greater than number of electrons, right? And 30.4% more neutrons than electrons. Similar question. So how are we going to proceed? Again, we are going to consider the number of protons to be X. Electrons are going to be 3 less. And number of neutrons is going to be whatever is the number of electrons, 30.4% of that number add to this will be giving us number of neutrons. So when you solve, you're going to get mass number is proton plus neutron. 56 is the mass number given. Protons we have assumed to be X, and neutrons we have received the number here. So solve this, and finally you'll get X to be equal to 26. It's all calculation. You'll try that yourself. So number of protons, X was supposed to be number of protons. Number of protons is 26. Electrons, you subtract 3, you get 23. So what will be the symbol? It will be Fe, and number of protons is 26. Mass number is already given 56 and 3 units of positive charge. So this is the symbol of the species. Finally, isotones is another term which is not given children in NCERT, but it's similar to isotope, isobar in that category. So I'm just defining it. Atoms of different elements again with different atomic number, different mass number, but the only important thing is they have the same number of neutrons. That means A minus Z. A is neutron plus proton and Z is proton. So if you take this N plus P minus P, it is going to be equal to N, number of neutrons. Isotones will have same number of neutrons. For example, if I have these 3 species, they have different atomic number and different mass number. But if you look at the number of protons in each case, 16 minus 8, number of neutrons is 8. 15 minus 7 neutrons is again 8. 14 minus 6 neutrons is again 8. So these 3 are isotones. Different atomic number, different mass number, different element, but the number of neutrons is the same. Okay, then isoelectric species. What are isoelectronic species? Isoelectronic species are those which have the same number of electrons. And when we use the word species, species means it can be atoms, it can be molecules, it can be ions, cations, anions, anything. Species is the general term. Species having the same number of electrons, right? So as an example, if we just take up this, we have these ions. In each of these, if we just write down Z, Z means atomic number. The atomic number of aluminium is 13, magnesium is 12, sodium is 11, neon 10, and so on. I've written all the atomic numbers. And then number of electrons, if I want to find, since it's a 3 positive charge, that means number of protons will be more than number of electrons since there's a positive charge. So 3 positive charge means 3 less electrons. So number of electrons is 10. Here number of electrons will again be 10 by 12 minus 2. Whenever you have a positive charge on the species, to find number of electrons, subtract that positive charge from Z. Right? So till here we get 11 minus 1, 10. Neon, no charge, so the atomic number is equal to the number of electrons. Fluoride ion, atomic number is 9. But there's a one negative charge means add one electron to it. So number of electrons is 10. Similarly, 8 plus 2 is 10. 7 plus 3 is 10. Okay, so what do you find? All these are isoelectronic species. Why? Because they have the same number of electrons. Atomic number was different, but the number of electrons are the same. So these are called isoelectronic species. So here I'm asking you a question. This is again a very, very possible and a probable question for school exams. Write isoelectronic species of cyanide ion. So how can we start? Cyanide ion. The first thing that I can do is to create the species. I will just consider carbon is, what are the total electrons here? Carbon 6 plus nitrogen 7 plus 1 due to negative charge. The total comes out to be 14. So if I count N with the negative charge together, I can write it as O. Why? This is 6 and this is 8. I just put 7 plus 1, 8. Atomic number 8 belongs to oxygen. So instead of N negative, I write O. So again, the number of electrons are the same. Similarly, what if I add this 1 with this 6? It becomes 7. That means nitrogen. So N2 will also have 7 plus 7, that is 14. This will also be isoelectronic species. And then I can replace that negative charge with H plus. So this is 1 plus 6 plus 7. This is again 14. And if I look at an element with atomic number 14, what is the element with atomic number 14? The one which comes below carbon in the periodic table. So silicon. So all these species are going to be isoelectronic species of cyanide ion. This is cyanide ion. So if you think systematically, it becomes easier to track this. Okay. And then if the question is specifically give a diatomic molecule which is heteroatomic, or give a homoatomic diatomic molecule, or give an example of a triatomic molecule which is isoelectronic with cyanide, or give an example of an element which is isoelectronic with cyanide. So based on these questions, anything can be asked. So this is an important one, important example. Do practice this. So thank you. I hope you like this, children. I hope this helps you. Please learn everything that we've discussed here. These are all probable questions from first half of the chapter. Stay tuned, study well, and do like, share, and subscribe, children. And any comments, any changes you wish, please do that. Thank you. God bless you all. Closing for the day.